We want to describe the motion of this object in number 4. And we're asking, is it speeding up, slowing down, moving forwards, or backwards? So, let's be clear. Let's just do a tiny bit of review. Here's a position versus time plot. And again, this is position in centimeters. And I should have labeled that. And this is time in seconds. So let's just go back to constant velocity for a second. So here's graph A, and here's graph B. If you recall, B is slower than A because its slope is less steep. So the trend for graphs here is, how do you know if this graph is speeding up, slowing down, moving forwards, or backwards? First, we see it moving in a positive way. So it's definitely moving forwards. And it's going from a steep graph to a flat graph. And less steep means slower. So it's slowing down. Okay, so it is moving forward. And it's slowing down. Next, at 4 seconds, the slope here is flat. And that means, so at 4 seconds, the slope is flat. And a flat slope means v equals 0 on a position graph. Because if you remember, since slope is the velocity, if slope equals 0, that means velocity is 0, and the slope at 4 seconds is flat. Now, the average velocity from 0 to 2 seconds, let's be clear, okay? To get the average velocity, and let's go back to the formulas here, because I know there's a couple here on the thing. So here we go. Right here, the average velocity is given by the displacement over the time that passes. So delta x over delta t, or just t. Going back to the problem, I'm going to actually use that here. So the average velocity from 0 to 2 seconds, I'll just do this right here. At 2 seconds, I'm at 2, 4. At 0 seconds, I'm at 0, 0. And in a second, I'm going to need this coordinate here, which is 4, 5. So let's get these average velocities. I'll zoom out just a little bit here. So the average velocity from 0 to 4 seconds is going to be delta x over the time that passes. 0 to 2, that's 2 seconds. So that'll be delta x over 2, which is going to be, when I do this, 4 minus 0, reading the position coordinate, 4 minus 0 all over 2, and that gives me 2 centimeters per second. And then from 2 to 4 seconds, we'll do the same thing. That V average is, I do 5 minus 4 over 4 minus 2, taking the difference. Basically, I'm getting a slope, because velocity is a slope. I'm getting kind of an approximate or an average slope here. So that's going to be 1 over 2, which is 0.5 centimeters per second. And the way this shows that we are slowing down is, as time goes on, V average gets smaller in size. Because look, I'm at 2 centimeters per second, and then I'm at half a centimeter per second, let me make sure I have that right. Let me double check this number. I said it was 4 minus 0 over 2. Let's be careful. That's not 0, 0. That's 0, 1. So let's go ahead and correct that. That's 4 minus 1 over 2, which is 1.5 centimeters a second. And this is 5 and 4. Yes, so we're good on that. So the average actually gets smaller in size as time goes on. Now, what might the velocity versus time graph look like? We actually did these graphs in class if you actually look at the notes on the graphs that I gave you. So since I'm starting off going forward and I'm fast, so I'm fast here, and then I'm slow at the very end. So this is at the beginning I'm fast, and at the end I'm slow, actually stopped. So slow and stopped means I'm at 0. Fast means I'm above the line if I'm going forwards, which I am. And so I'll draw these 2 points, and then I'll just connect them with a line like that. And that's how we will draw the velocity versus time. So that is question number 4.